So let's do a couple calculations involving pH. So let's figure out what the pH of a solution with a hydronium concentration is 1.45 times 10 to the negative fourth. So now we know that the pH is equal to the negative log of the hydronium, or H+, but in this problem it gives us hydronium. And the problem states that the concentration is 1.45 times 10 to the negative fourth. Okay, and so we can calculate this fairly easily. Okay, so we've got negative log of 1.45 times 10 to the negative fourth equals 3.83, and we usually use the same significant figures as the concentration value, and so that's going to be 3.84 as our pH. And one thing we should also be able to determine is whether or not this solution is acidic or basic, and since this pH is less than 7, it is acidic. Alright, so another thing we can do using this equation to actually determine the hydronium ion concentration from the pH. Alright, so for this solution we measure the pH to be 6.25. We want to know what the hydronium ion concentration is. And that's just going to take a little bit of algebra and use it into our equation. So we know that the pH equals negative log of H3O plus. And what we really want to know is, okay, we know the pH. We want to figure out the hydronium ion concentration. And so what we need to do is use our algebra to get rid of this log. And so what we do is we take the anti-log of both sides, and in most calculators it looks like 10 to the. And actually, I skipped a step. I also want to get rid of this negative, and so really I want to multiply both sides by a negative. So negative pH, and that will turn this into a positive. And then I want to take the anti-log of both sides. And what that does is it cancels out the log. And so the equation turns into H3O plus ion concentration equal to the anti-log of the negative pH. And so we can throw this into our calculator. We just need to find the anti-log button, and usually that is the second log button. So there's my log button. I hit shift second, and there's my little 10 pop up, and 10 to the negative 6.25. 10 to the negative 6.25. That equals 5.62 times 10 to the negative 7th molar. The units don't come out of this equation, but we know that brackets equals concentration in molarity. Okay. So the other thing we need to talk about is the hydroxide ion concentration, how we could figure that out, or use that to calculate the pH. So there's a couple of ways we can do that. All right. So from the Kw equation, we could rearrange that to equal that 14 is equal to the sum of the pH plus the pOH. That's a very common equation to use when you have the hydroxide ion concentration. Okay, what's the pOH? Well, it's the same thing as the pH, except for that, of course, it is the negative log of the hydroxide ion concentration. Okay, and so what we could do is say we have a 0.125 molar sodium hydroxide solution. Okay, we want to figure out the pH of that. Right, since this is a strong base, we know that it ionizes 100%, dissociates 100% because it's an ionic compound. So if that's the concentration of sodium hydroxide, we also know that is the concentration of hydroxide ion. So the hydroxide ion is 0.125 molar. Okay. pH, that's what we want, but of course we know the concentration of hydroxide. We don't know the concentration of hydronium. So what we can do is calculate the pOH first and then use this equation to figure out the pH. So pOH equals the negative log of 0.125. Throw that into our calculator, negative log of 0.125. That's going to give me 0.903. And of course, my pOH, 0.903. And then if I want to find the pH, I would rearrange that above equation to say that pH is equal to 14 minus the pOH. And then just simply calculate that. 14 minus 9.903, and so that's what, 13.097. And that's the pH of the solution. And of course, that is greater than 7, and so that is a basic solution, which isn't surprising because we have a solution of a strong base. All right, one more thing to talk about, and that is buffers. Buffers are extremely important in biological systems, as well as doing lab work chemistry. A buffer is a solution that is able to minimize changes in pH. All right. It consists of a mixture of a weak acid and weak base. And they have to be weak. They cannot be strong, or else they'll just neutralize each other. But because weak acids and weak bases set up equilibrium, we can have both species in the same solution. Okay? And so, let's make a buffer. All right, some ions that are extremely important in your blood pH is, of course, hydrogen carbonate and carbonic acid. All right. Turns out hydrogen carbonate is a weak base because it can accept a proton to form carbonic acid. And then, of course, carbonic acid is a weak acid. Okay. So we said it can minimize changes to pH. So we have to think about how we would change pH, either adding acid or adding a base. So if an acid was added, say hydrochloric acid, a strong acid. Hydrochloric acid would, if HCl were added to this buffer system, it would be neutralized by the weak base. By HCO3, hydrogen carbonate ion, to produce carbonic acid plus chloride. And then if a base were added, let's say a hydroxide, so sodium hydroxide, which of course dissociates 100%, and so really the base that's going to react is the hydroxide. What is going to neutralize the hydroxide? Well, of course, we've got carbonic acid in the solution, which can neutralize the hydroxide. The hydroxide will accept a proton from carbonic acid to make hydrogen carbonate plus water. So that's the mechanism in which buffers can minimize changes in pH because they consist of a mixture of both a weak acid and weak base. If acids or bases are added to the solution, the pH is minimized by the fact that there's an acid to neutralize any added base or a base to neutralize any acids.